To understand the workings of the machine learning algorithms, it is often helpful to study two-dimensional or even one-dimensional data. That is data with only one or two features. While in practice, the datasets usually have many more features, and it is hard to plot high-dimensional data on two-dimensional screens. So here we will demonstrate some of the very simple examples before we can move on to more real-world dataset. First, let's take a look at two-class classification problem in two dimensions, okay? Here we can generate a synthetic data using the scikit-learn's make-blob function. So we import matplotlib numpy. From scikit-learn dataset module, we import the make-blobs function, okay, that will generate data for us. So x and then y. You can see the first 5 samples. Each sample has 2 dimensions. And total number of samples here that we generated is equal to 100 samples. Y's are labels. They're 0 or 1, binary classification problem. We can quickly visualize the scatter plot as follows. So these are the 100 examples we just generated. Blue and then a red squares. Okay, the classification is a supervised task, and we are interested in the performance of the model on unseen data. Okay, so one of the first steps in estimating the model from data is splitting. We will use a training set, okay, that the learning algorithm uses for fitting the model, and then test set to evaluate the generalization performance of the model. Okay, we are familiar with the train and test split function of scikit-learn model selection module. We will use train test split function of scikit-learn to split our generated data into a test and train set. We will use only 25% of the 100 examples we generated as a test set. The remaining are the training set. There are 2 stages, right? We have training data, training labels, 70% of our selected generated data. We select the model based on the data, and we will evaluate the model's performance on test data. Once the model is learned, we will pass the test set to generate the outputs of the model. And given the labels, the following labels, we can compare the predicted labels with the given labels to evaluate the model's accuracy or the generalization performance of the model. Now let's try to import logistic regression to perform model training and evaluation. Okay? Note that all models in scikit-learn have a very consistent interface. For example, logistic regression, which is located under scikit-learn.linear model, has a specific set of functions or methods which is consistent across all other models available under sklearn linear model. Next, we instantiate the estimate object, logistic regression, as a classifier. Let's also take a look at our train data shape. 75 training examples. Each example has 2-dimensional feature. Why train? Y's are labels. To build a model from our data, that is, to learn how to classify new points, we call the fit function with the training data and the corresponding training labels. Desired output for the training data points. Okay, so if we take a look at the .fit method of our classifier object, we can find its documentation. So X is the input training examples, should have the following structure. So rows corresponds to the number of samples, features are in the column. So 2-dimensional array, and Y labels. Right? So we pass our X train, Y train. And if you do run this, the classifier already is trained on these examples. Okay? All the weights of our logistic regression is stored inside this object. We can take a look at the estimated or learned weights at classifier.coef_. Since we're dealing with a 2-dimensional input data, we expect to have 2 weights, right? Some additional information about the parameters of our classifier objects, such as regression, can be found here. And the solver is an optimization tool that performs the stochastic gradient descent in minimizing the cross entropy function. We also see some tolerance, penalty, maximum number of iterations, and additional information. So now once the classifier is trained on X train, Y train, and has obtained the following weights, we can evaluate this classifier on test dataset. So one thing to note in this example is that we are not passing our Y test labels, right? We are evaluating, and the prediction will consist of the predicted labels. We can check, for example, here. So prediction corresponds to ones or zeros. This is the classifier predicted from the data X test. The predicted labels. We have Y test already available, okay, from our allocated X test. So we can compare. Most of them agree. So most of the predicted labels correspond or are equal to the given label, except these ones. Okay, our model predicted the second example as 0, but Y is 1. Also here, we see some of the examples in our X test has not been correctly classified. So to evaluate the performance of our classifier, we can use the accuracy metric. Okay, what does accuracy do? So we are performing point-wise comparison of predicted and test available label here. Well, the output of this will be, let's say, the Boolean values, so true, true, false, false, false. And false, those points correspond to mistakes that has been made. We will sum truths and then divide by total number of samples available. Then we will get the accuracy. So we can relate it to 84% accuracy. There is also a convenient function called score that all scikit-learn classifiers have. This will allow us to compute the accuracy directly from the data. All right, so if you run this, we get the same 84% accuracy. The 1 is maximum, 0 is less. So we can convert it to percentage. All right, sometimes it's helpful to compare the generalization performance on test set to the performance on the train set. What we are doing here is that we are evaluating our trained model on, again, X train and Y train. And as you can see, the accuracy goes up 97%. So all of the training examples have been, most of them have been classified correctly. We know that logistic regression is a linear model, right? Which means it will create a decision boundary that is linear in input space. In 2D, this means we find a line to separate blue from red. We can visualize. So we are plotting the scatter plot of our X data for two classes. Okay, and then visualizing the classifier. The logistic regression corresponds to this line on 2D on these simple examples. Okay, so here, as I briefly mentioned before, we have W1, W2, and then bias. We're dealing with two-dimensional input space. So we have intercept, okay, can be found here, the optimal intercept, and then the weights that has been learned. Another popular and easy to understand classifier is called KNearest Neighbors, in short, KNN. It has one of the simplest learning strategies. For example, given a new unknown observation, look up in your reference data or database which ones have the closest features and assign the predominant class. Okay, so KNN is a non-parametric classifier. That means it stores all the training data, and each new instance X is classified using a majority vote over its set of k nearest neighbors, which is computed using a distance function, any distance function. So the classification function of k and n is as follows, as simple as this. So find the y that maximizes the sum. Graphically, right? In KNN, we use different neighbors. For example, if those stars are our test examples, and then their color is determined by the closest sample. In this case, first one neighbor. In order to identify the label of this example, we find the closest point to it, and we're using the metric distance function and assign the label accordingly to the closest example. In this case, the closest point is this. Well, for the given test example, in this case, is closest to the following point. So number of neighbors is another hyperparameter that we use in KNNs. So if you have 3 neighbors, okay, given one example, calculate the 3 closest examples, a distance, okay, to the nearest points. Well, in this case, one of the examples says it's blue circle, the other 2 says it's red. So the label of this example will be decided based on the majority vote. Therefore, it is red now. For this given example, find the nearest 3 neighbors and calculate the distance and assign the label based on the majority vote. Okay, so 3 neighbors, closest neighbors are the following points for this example. Since 2 of them says it is red, the label will be red. What about the following example? So we have 1, 2, 3 neighbors closest, all of them are blue. So it will be classified as blue. Okay, and we can visualize here the decision boundary found by using the one neighbor only, 3 neighbors. Okay, we can go up to 9 or even more neighbors. So the label of this point will be identified by the majority voting of the 9 neighbors around this point. So in general, KNN can work with any distance function, which satisfies a non-negativity between 2 points, right? 2 examples. Distance metric should always be positive. Alternatively, KNN can also work with any similarity function, okay? If you can come up with a similarity function that shows that these 2 examples are similar by according to some criteria, you can use it. So Minkowski distance is one of the commonly used metric for evaluating the distance, okay? It is also known as LP norms. In this case, we have 2 vectors, 2 examples represented as a vector in d-dimensional space. The Minkowski distance has a parameter p, okay, the LP norm, and it is a metric defined as follows. So distance of x and x prime is equal to the following, the norm between x and x prime and p. Well, if you open up this, it's basically the following term, sum across all d between 2 points raised to the power of p, and this is 1 over p, right? So if p is equal to 2, we recover our Euclidean distance. If p is 1, then we call also it as a Manhattan distance, right? When the p is infinity, this metric is called Chebyshev distance. And the brute force KNN can be described as follows in 3 steps. So given any distance function d, the brute force KNN works by computing the distance between xi and x star. Here x star is a target point to all of the training points xi. Second, sort the distances, sort the calculated distances, and choose the data cases with the k smallest distance. Okay, so to form the neighbor set defined by n k of around x star using a similarity function is identical, but you can select the k most similar data cases. Basically, we're describing these. All right, so once k neighbors are selected, apply the classification rule. All right, so in scikit-learn, we have similar interface to KNN, same as logistic regression above, but it is located under scikit-learn.neighbors. So let's import it, instantiate. Here, we have a parameter of our nearest neighbor classifier. Here, we define it as 1. We can do it as 3. Well, it depends. Similar to a logistic regression object, KNN comes, and many other estimator object in scikit-learn has .fit and .predict, right? .can and .fit performs fitting the model on the training data. Now let's take a look. So based on, one neighbor, single neighbor, we have derived the following decision boundary on all training examples. What happens if you do it 3? Can we see the change? Yes. We can see some changes in decision boundary. Fit? Oh, okay. The more neighbors we involve, the more linear the decision boundary gets. So next step is, once we train a model, we can score. We can get the accuracy. All right, or we can KNN predict X test, and these are the predicted labels, right? And then Y test are the given available given labels, right? Actual labels. So we can see some differences. This leads us to 88% accuracy. Now we can use KNN classifiers on our iris dataset. Do this exercise yourself, okay? Just to experiment with. In the second part of the supervised learning example using scikit-learn, we will take a look at the regression analysis. In regression, as we know, we are interested in predicting a continuous output variable, in contrast to nominal variables, which we were predicting in the classification example above. Let's again start with a simple toy example with one feature dimension and one target variable, and create a dataset out of sine curve with some noise. Let's do it. This is our X. We're generating sinusoidal Y data with noise. Okay, as we can see, the data looks like the sinusoidal function. Here we have X and then Y. Let's use a linear regression model for this. This is a simple model which fits a line to the data. And again, one of the simplest model is a linear one that simply tries to predict the data as lying on a line. One way to find such a line is to use a linear regression. The interface for the linear regression is same as for the classifiers before. That's why we say that all the interface to the estimator object are very consistent in scikit-learn. The only difference in regression is that y is not a, let's say, binary value. It's a continuous. Okay, so let's try to take a look at our dataset. So we need to make the following changes to our dataset. Initially, we had just one tall vector, but scikit-learn accepts or wants us to provide two-dimensional array. So we convert from vector to two-dimensional array. Here, 100 examples, each has one feature, right? We can do the same split, train test split with the following ratio: 75 for training, 25 for test, okay? And import linear regression from scikit-learn.linear model. And then do the same fit, regressor.fit after instantiating on next train. So once training is complete, we can take a look at the weights, the learned weights from data. So one variable, one weight coefficient, and intercept. Okay, since our regression model is a linear one, the relationship between target y and then feature x is defined as follows. Y, we have weight input. Okay, we're dealing with one-dimensional input data and intercept. Then y will be predicted y. And plugging, let's say, in the mean max values into those equations, we can plot the coefficients. Here, sinusoidal data and linear regression. So what we can say here, so linear regression is a linear model and therefore is restricted to capture these complex patterns, right? If you use second, third order polynomial, probably we can fit a nonlinear model to exactly capture the sinusoidal nature of our input. So, similar to the estimators for classification previously seen, we use predict method to predict the target variable y. And we expect these predicted values to fall onto the line that we previously plotted. Let's run this. And then, all right, so this is predicted fit hypothesis, and these red circles corresponds to the predicted labels. In this case, we are trying to predict the labels of X-ray. And as we can see, the line is able to capture the general slope of the data, but not many details, right? It cannot capture the sinusoidal data. So now let's try to predict the test using the linear regression, right? So if we do that, we can see X test shape 25 by 1, and then, 25 by 1, and then 25. And if you plot this, let me run, okay, X test, Y test, label data, prediction. And then this is a line that has been fit. We can see again the labels of those test examples lie along the fit line, the hypothesis. So scikit-learn provides an easy way to estimate a prediction quantitatively using the score method. But here in the regression case, we're interested in R squared score. And we also know that the linear regression, uses mean squared error as another metric, right? MSE, which is simply the difference between predicted and then 2 raised to the power of 2. So if we evaluate the performance of our linear regression, we'll get the following. So it is about, let's say, 79% accurate. All right, now you can do the following exercise. Add a feature containing to our sinusoidal and redo the fit. Try to visualize the predictions with the new richer yet linear model. Okay, try this. All right, so we can apply KNearest Neighbor for regression problem as well. So for that, let's import the KNeighbors regressor from scikit-learn regressor module, and then perform the fit. Instantiate, define the number of neighbors, and then fit. Okay, and you can try to predict. So data, and then predicted ones, predictions. So as for the classification, the k-nearest neighbor base for regression simply takes the output of the nearest point, okay, or the average several nearest points, the average of several nearest points, and then define the output y. Well, k-nearest neighbor for regression is less popular than for classification, but still a good baseline. And then once we have this, we can try to predict. As you can see, the labels of those predictions are based on the nearest neighbors. Okay, we are here considering only single neighbor. And we can see that the test set, the performance of k-nearest neighbor on test set is much better. However, our estimate look much better than before. So here you have another exercise. Compare the k-nearest neighbor regressor and linear regression on Boston housing dataset. That comes with the scikit-learn package. Okay, you can easily access fetch. Okay, it's located here. scikit-learn dataset load Boston. In the previous sections and the notebooks, we split our data into two parts, a training set and a test set. We then used training set to train our model or to fit our model. And we used the test set to evaluate its generalization performance. In other words, how our model performs on new unseen data. However, most oftentimes, the labeled data is limited. And using this approach of splitting into training and then testing may not be the best option. Okay, because we will only have 75% of the data used by our model, and we're leaving 25% for test. So a common way to use more of the data, the limited data, to build the model, but also get a more robust estimate of the generalization performance is cross-validation. We know about this topic. In cross-validation, we are splitting the data differently. In other words, The data is split repeatedly into training and non-overlapping test sets with a separate model built for every pair of train and test. And then the test set scores are used for estimating more robust model. Okay, the common way to do a cross-validation is, we know, called as k-fold cross-validation, in which the data is split equally into k equal size folds. Often this k is 5 or 10. And then for each iteration, one of the k-fold is used as test data and the rest as training. Okay, for example, we take all data, split into equal 5 sets. We use fold one set of the data as test, remaining as train. Second, we fit another model on the 4 sets except the fold 2, right? And we repeat them. Repeatedly fit the model. And this way, each data point will be in the test set exactly once. We are using this, right? And we can use all but case of the data for training. Let's try this in example using the KNearest classifier algorithm on iris data set that we know. Let's load the iris, instantiate the KNearest neighbor classifier. All right. And then take a look at the Y labels of our iris. So we are dealing with 3-class classification problem. And the labels in iris are sorted, which means that if we split the data as illustrated here, the first fold will only contain 0 labels, while the last one will contain the 2s, right? To avoid this problem, we can shuffle the data, okay, and mix all the, or randomly shuffle the data so that the first 50 examples is not only those flowers, are not only those flowers correspond to 0 label, okay? Now we can implement the cross-validation. So 5-fold cross-validation, we get the number of samples, the links. Here we have 150, and we divide by 5, which will split equal our 150 examples into 5 equally sized sets. And we collect the scores of our model, KNearest neighbor, and then we also have the mask parameter. So for each fold in range 5, okay, get the data, extract the test, okay, test, X test, Y test, train on Y train, and evaluate on X test. Here, fit score, right? Train on X, train, evaluate on. So we do repeat the loop. So if you do that, so we train KNearest neighbor 5 times, as follows. First, train on these, test. Second loop, train on the following, and then test on this, and so forth. Now we can take a look at the mask. And by the way, so we also collect the score of each fold. Okay, at each fold, we will have one score. First, second, third, fourth, and at each iteration, we can take a look. So here, so first 50, let's see, 30 examples, right? This black dashed line correspond test. And the remaining are used as train. Second, this one is used as test, remaining as train. So here index 0, 1, 2, 3, 4. So we do 5 iterations. And if you want to take a look at the scores, we do for each fold. So first one corresponds to the score on this left out X test. Second one on this. Third, okay, on this set. Fourth on this. And fifth. If we take the average, we will see the average performance of KNearest neighbor classifier on iris dataset is 96. 1 means perfect. So I always use percentage just to relate. So 96% accurate. So as we can see here, there is a a rather wide spectrum scores from 90% to 100. These are, okay, all correctly classified. So doing cross-validation will give us a better estimate of our classifier. Since the cross-validation is a very common pattern used in machine learning tasks, there are functions to do the above for us with much more flexibility and less code. Okay, we can, scikit-learn provides us performing this cross-validation much more efficiently. So scikit-learn model selection. This module contains a lot of useful functions for us for performing, again, model selection tasks. It has all the functions related to cross-validation. The easiest function is cross-val score, which takes an estimator object and a dataset xy and provides us the performance of our model. Well, internally, cross-val score is doing the cross-validation. Right, so if you run this cross-validation score, pass classifier, our data, and scores, these are 1, 2, 3, 4, 5 score. And by default, cross-validation score uses 5-fold cross-validation. You can define here as one of the parameters as fold, okay, 10. Let me quickly check. Yes, CV. Okay, so CV we need to define as the cross-validation parameter. 5-fold, default is 5-fold, so you can do it 10-fold, also define a stratified cross-validation. All right, and then we can check, perform this cross-validation. And there are also helper objects in the cross-validation module that will generate indices for all kinds of different cross-validation methods, including the k-fold. Let's take a look. So from scikit-learn model selection import k-fold. This is stratified k-fold, shuffle split. So if you define the stratified k-fold with 5 splits, okay, and then I get the train and test with a split of iris dataset target, we can get the indices in a stratified form. And we can try to visualize, all right, as follows. So stratified k-fold tries to maintain the ratio of different classes in the data, right? How about this? While in the original k-fold, they don't use the labels. So by default, the cross-validation score uses stratified k-fold internally for classification, which makes sure that the class proportions in the dataset, okay, are reflected in each fold. If you have binary classification dataset, then 90% of data point belonging to one class would mean that each fold contain 90% of data points would belong to, let's say, 0 class. And if we just use k-fold cross-validation, it is more likely that we would generate a split that only contains class 0. Therefore, it is generally important or good idea to use stratified k-fold method. And also it's important to note that stratified fold would also remove the need to shuffle iris dataset as we did manually. Okay, so we can see that in the following example. All right. So in this case, we keep in mind that increasing the number of folds, here 10, will give us a larger training dataset. However, it will lead to more repetitions. Therefore, slower evaluation. So we need to train the model 10 times if we increase to 10. Right? Another helpful function in cross-validation is shuffle split. This function generates with a cross-validation generator, right? Simply splits of a random portion of data repeatedly. This in turn allows us to specify the number of repetitions and the training set size independently. So all these dots are the test X test, right? First fault, second, third, fifth fault. So if you want a more robust estimate, we can increase the number of splits, 20. Right. Another example of using a cross-validation score with the following CV object, which gives us shuffled split. So I ask you again to try the following exercise. Perform three-fold cross-validation using a k-fold class on the iris dataset without shuffling the data, and then try to explain the result. Now, let me just summarize the scikit-learn's estimator interface of features. So scikit-learn strives to have a uniform interface, as we said already, across all methods. And given a scikit-learn estimator, this is an object, either this is your KNN, logistic regression, linear regression. The following methods are available. So model, okay, this is your estimator object. .fit performs training on the data. We have seen the following examples. For supervised learning, we have X and Y. For unsupervised, we train the model using only the X. And we also have, all estimators have the predict. Okay, once we fit a model on training example, we can use model.predict, given a training model, predict a label of new set of the data. We also have this predict proba. This is predict probability for classification problem, similar to predict. And here, the output of this .predict is the labels. Okay, in this case, we have the probability of that label. We also have some other methods, let's say decision function. For classification problems, some estimators provide an uncertain estimate that is not a probability. So for binary classification, if the decision is higher than 0 or equal, means positive class, while negative means negative. So these can be related to a sign function. Model score gives us, what's that? So score, right? The accuracy. For a classification, this is between 0 and 1. For regression, usually it's a R-squared score. And we also have a model transform. Well, model transform method is usually used for feature selection, pre-processing, dimensionality reduction method. It's not related to machine learning. We also have several unsupervised estimators, which we didn't cover. So they also have, unsupervised estimates have transform, fit transform, predict probability, and then score. Okay, this table should give us more details. So model predict is used in classification, regression, and clustering estimators objects, while model transform is used in pre-processing, dimensionality reduction, feature extraction, feature selection estimators, right? So predict, transform. We also have fit, right? These are all in addition to the model.fit function.